How does a switch-capacitor amplifier work, and what are its application and use cases are discussed in this brief tutorial video that tries to answer these questions using this example of inverting and non-inverting amplifier implemented with switch capacitors. So we would like to see how this circuit is working and what are the main components and choices for them. In this example, we have one op-amp in the circuit, we have two passive capacitors C1 and C2, and then we have 5 MOSFET transistors as NMOS switches that are used in this circuit with proper application of the right clock phase to them. You can see that 3 of them are connected to this clock 1, and 2 other transistors are connected to a second clock, that is clock 2. So these clock 1 and clock 2, they are related to each other. I will talk about it. So in the first part of this video, I would like to talk about why we need this seemingly not simple circuit. If you are comfortable with that and you would like to just see the computation of the voltage gain for this circuit, then you can just bypass the first portion of this video and jump to maybe from the middle of the video that talks about the computation of the gain in this circuit. Okay, so reasoning. The reasoning is, well, if we are supposed to implement, let's say, an inverting or non-inverting amplifier in the form of an active amplifier using op-amp, the well-known structure is as simple as this. We have input voltage, and then we have the simple op-amp in an inverting amplifier topology in which we have resistor R1, R2, and then, for example, effectively the positive or non-inverting input terminal of op-amp is grounded. Op-amp is properly biased, and it's in with the negative feedback because output is connected to input inverting terminal as an indication of negative feedback. Virtual short therefore is valid for this op-amp, which means the voltage at positive terminal should be equal to voltage at negative as long as this op-amp is enforced by negative feedback into the linear region of operation, not saturated. So here is 0, therefore effectively because of virtual short, this terminal is also forced to be at 0, or what we refer to as virtual ground. Writing a KCL here, the current going this way should be the same for R1 and R2. That means given the voltage drop across R1 is V in, given the voltage drop across R2 is negative V out because of the polarity compared to V out, it's easy to compute the well-known gain for the inverting amplifier, which is V out over V in equal to minus R2 over R1. That's well known, nothing new about it. I just wanted to confirm that this is what we are chasing now. If this is theoretically very simple and good circuit, the problem in practice is, let's say if in a chip or integrated circuit you're interested to get a gain of, say, negative 200 from this inverting amplifier, and inverting is because of the negative sign. Okay, the problem now is, for example, let's say because of the fact that you would like to have a minimal input current that is taken from the input source, you would like to have the resistor R1 at 10 kilo ohm, not less. And let's say as a result of the target gain, the 200 you have in mind, since denominator R1 is 10K, you would need to have R2 to be about 200 times 10K, which means you would need an R2 of 2 mega ohm, which is pretty large. Here's the problem. In order to implement this fully in a chip, including both all the components, or let's say the transistor circuit inside the op-amp, and also all the resistors R2 and R1 in a chip, now the problem is the size of these resistors. Even 10 kilo ohm would require a large area in a chip to realize a meaningful and accurate resistor, let alone the 2 mega ohm, which is completely unacceptable as a passive resistor implemented in a chip, requires a huge area, and these things would actually come up with considerable inaccuracy and variation due to, let's say, thermal variation and all other parasitic effects and associated, let's say, parasitic or capacitance effects of these resistors. So effectively what I'm trying to say is implementing these sizes in a chip as a resistor is prohibitively expensive, and also sort of are accompanied with a lot of parasitic effect and non-idealities. So how do we avoid this while at the same time still getting a gain of, let's say, negative 200? That would be the thing that we realize using switch capacitor circuit. So the motivation is now clear. We want to move away from this circuit that is simple but the problem is it's not chip friendly to a circuit that is seemingly a little bit more complicated based on switch capacitors that hopefully is very chip friendly implementation. So how does it work? Okay, so let's start with first noticing the relationship between clock 1 and clock 2. So it's very important to notice that these are not just random clocks. These are same period clocks, meaning that both of them, they have the same periodicity or frequency, but let's say I'm going to shift the clock 1 to compare it to the one below. So it looks like exactly like this. So let's say something like exactly this, just as an example. Okay, so what happens is during the time that when you compare these two clocks as an illustration, and so this is clock 1 and this is clock 2. So when you compare these two clocks, they have exactly this sort of a relationship. So they have the same frequency and period. But when the clock 1 is high, during this time, the clock 2 is definitely off. When clock 2 is high, then the clock 1 is off. So they do not overlap. At the same time, there is a preference that practically there should be a gap between the falling edge of clock 1 and rising edge of clock 2, and vice versa. Between the falling edge of clock 2 and rising edge of clock 1, there are dead zones, so that we make sure that there is no time, even in practical implementation, when clock might suffer from some shift or offset. We don't want all the 5 transistors to be temporarily on at the same time just because clocks happen to suffer from some offset. So practically speaking, we would like to have sort of a gap between them. Okay, so that's the relationship between clock 1 and clock 2. But why do we have this relationship? The answer is this. So I'm going to show it here. Let me just make sure that, okay, all right. So the answer is here. When clock 1 is on, so in this circuit, when clock 1 is on, clock 2 is off. So what happens is in the implementation that we have, when clock 1 is on, so basically when we are in this time period, in this gap, then this switch, which is a very small transistor, and we can just make the assumption it's like an ideal switch. In practice, it's not ideal switch. There is a non-zero resistance or R-on associated with it. But let's make the assumption that R-on in this circuit is negligible. So effectively, when this turns on, this MOSFET and MOS switch turns on, it's as if effectively from the perspective of circuit like a short. And when it is open during the time that clock 1 is shut down or off, this transistor is like an off switch with an infinite resistance. So we are modeling this MOSFET transistor or NMOS switch as ideal switch in the circuit. Okay, so when the clock 1 is high, during this time, this is on, this switch, and therefore we can model it as a short. So the same thing goes with this one. Let's say if this is T1, if this is T2, and if this one is T3. So during the time that clock 1 is on, then T1, T2, and T3 transistors are all on switches with effectively 0 resistor equivalent. So the circuit looks like then, so when clock 1 is on, then the circuit looks like this. We have V in, and then we have a switch that is on for transistor T1. So, and then we get to this switch T4 is off, because during this time the clock 2 that is driving the gate voltage of T4 is off. Therefore T4 switch is off, and we can model it as an infinite impedance, which means this is caught. So there, as if this connection is not there, it's an open connection. The same thing goes with T5. When we are in the duration that clock 1 is on, then T5 is off. So the circuit, and effectively what happens is the circuit looks like exactly capacitor C1, and then goes to op amp negative plus. We have connection to ground from the positive terminal, and then we have a cap C2 that is grounded on one side, and on the other side is connected to virtual short. And then we have a short connection because T2 switch is short and on, and we have connection to the output Vout. We don't care about RL because that is not defining the gain of the amplifier. Okay, so what is happening is for C2 on one side during this scenario, we are connected to ground via T3 switch, and then on the other side, because of the virtual ground of the negative terminal that is in 0 volts effectively, C2 is completely discharged to 0. There is nothing going on. Now, what happens is the circuit tries to naturally charge C1, and the output of op amp effectively is grounded, so is 0 volt during this time. We don't care, that's not the output we're gonna monitor. So as if output at this time is we don't care. So during this time, because of this current I that is flowing from V in, we are charging cap C1. So what cap C1 observe is there is a voltage drop across C1 that on one side we have 0 volt because of virtual ground. On the other side we have V in. So the voltage drop across cap C1, VC1 is just V in. Okay, so how much charge needed to have this voltage across C1? Obviously it's just the Q of C1, or charge across C1 with this polarity, should be equal to voltage across C1 times the C1 value itself. So voltage across C1 is V in, so it becomes V in times C1. That's the total charge on the plates of cap C1. Alright, this is the state of the circuit in this mode, and Vout is 0. We don't care about it because we are not looking at Vout at this point. But then what happens is, after clock 1 is done and clock 1 goes down to say the low level, then clock 2 goes high. So we are past this point. Now clock 2 goes high and stay high. So what happens is when clock 2 is on, obviously clock 1 is off. The same thing that I mentioned earlier, when clock 1 is on, clock 2 is off. Okay, so how does the circuit look like? So I'm gonna just remove this portion here because we talked about it. So I'm gonna remove it, but I'm gonna keep this circuit as a reference because it just reminds us what was the value of resistors that we needed in the circuit. So I'm gonna keep this as a reference. Now what happens is, let's take a look at the circuit when we have the situation of clock 2 is on and clock 1 is off. Okay, so the circuit looks like now this circuit. We have T1 switch off like a completely open circuit as an ideal switch, T2 off like an open circuit again, T3 off like an open circuit. So the only two transistors as switch that are on with an ideal switch would be T4 and T5 that are shown here. So what happens is the circuit now looks like during this let's say situation, it looks like this. So we have plus input non-inverting terminal of op amp is still grounded, and then we have the inverting or negative terminal connected to C1, our passive capacitor, and then via T4 as a short or let's say on switch, we are grounded on the other side of the C1. And then from the negative terminal of the input of the op amp, we go to C2. We don't care about T2 here because it's open, so the only thing is C2, and then T3 is open, so there is no connection to ground. But then T5 transistor or switch is on, an ideal switch, and therefore it's shorted. So that's T5, and then we go to output Vout. So now the circuit looks like as simple as this. The only thing is we know already that there is a charge VC1 equal to V in. So remember that the voltage on cap C1 during the previous phase is V in. So we have V in here already with this polarity. So, but what is the steady state requirement for C1? Well, you can see that on one side of C1 we should get to ground. On the other side we are at virtual ground because of the negative feedback of the op-amp that enforces effectively virtual ground. So we should get to 0 here as well. So you can see that when we get to a steady state, then the charge across cap C1 should become 0 because it requires 0 voltage drop across the C1 ultimately, because on one side we have 0, on the other side we have 0 as well. So what it means is we should have this current, this charge completely removed from C1. How is it happening? Well, the output of op-amp provide a current that goes like this. It cannot go any other place except through C1 and then to ground. So what this current that is shown in green is trying to do is it is now trying to offset the initial voltage V in. So it's trying to offset the initial voltage V in across the cap C1 by discharging whatever charge is on C1. But because of the law of preservation of the current and charge, whatever we remove from this one will appear here on C2 as well. So with this polarity, because we are charging things up, capacitors up with this polarity given the direction of the current. So we have QC1 moved over QC2, assuming that the cap at the output of the whatever practical cap at the output of op-amp we have is negligible compared to sizes of C2 and C1. So those are important practical considerations. So what happens is now we have basically just consider that we have C1 and C2 in this circuit. So what we have is now Q of C1 should be equal to Q of C2, which means C1 times voltage across C1 at the beginning of this process should become equal to C2 voltage on C2. Of course, the polarity is like this, which is matching the polarity of the output voltage, because we measure output voltage between output and ground. So this polarity of output is matching the polarity of the target charge on cap C2. Okay, so let's compute this. C1 times VC1 is V in, because we know that C1 is charged to V in, and then C2 times VC2, which is V out. So therefore we get V out over V in is equal to C1 over C2. This is the voltage gain of this switch capacitor circuit during when exactly we end up applying clock 2 after the application of clock 1 as discussed in this example. This is the moment we look at the output. Again, we have to just look at the output periodically at specific moments. We can only look at the output at those sort of periods or moments. Otherwise, the output is invalid. That's basically we are sampling output in this circuit. Okay, so what's the beauty of this? Well, we can realize the gain. This is actually a non-inverting amplifier, sort of a non-inverting switch capacitor amplifier. I'm going to show you the inverting version. So this is the amplifier that is matching what we used to see as this circuit in a active sort of non-switch capacitor design that was like this. So I'm going to show you the non-inverting amplifier version of the non-switch capacitor design, traditional design, that looks like this. So here we have R2, R1, V out, and then we have, let's say, the connection R1 to V in, which this resistor doesn't matter, it's only for matching, because for ideal op-amp there is no current there is no practically zero current going through the input terminal of op-amp because of near infinite impedance or practically infinite impedance. So Vn appears here, at the positive terminal, then because of virtual short Vin appears here, then there is a R2 R1 effectively in series. There is a voltage drop to get to V out, which if we just write the simple KCL at this node, we get to, or let's say KVL for voltage drop, we get to V out equal to just simply 1 plus R2 over R1 times V in, a positive gain basically. V out over V in as the voltage gain is 1 plus R2 over R1. So this is our voltage gain for the non-inverting amplifier. So this is inverting and amplifier, and this is non-inverting amplifier. So we are now effectively realizing this non-inverting amplifier using switch capacitor by this circuit, with the kind of a clock 1 and clock 2 applied, and with the relationship that clock 1 and clock 2 has, they have to with respect to each other, we realize non-inverting amplifier that has this gain. So if you were interested to realize a gain of 200 that we showed is problematic with respect to size of resistors, now with this one it's going to be super simple, because if we say AV is desired to be 200, then I can say, all right, let's set the C1 and C2 like this. Let's set, because the ratio of C1 over C2, C1 being here and C2 being here, define the gain. So maybe I'm going to select C1 to be, say, for instance, 100 picofarad. So C1 equal to 100 picofarad for as an example, depends on exact application you have in mind. And C2, let's say 200 picofarad for a gain of 200 and 1 picofarad. So that exactly going to give me a gain of 200. So what is the benefit of this? Well, the sizes of cap 1 picofarad, or even let's say if you want to be even more realistic, super practical in terms of chip design, let's say 100 nanofarad, which is 0.1 picofarad. So maybe I just say sorry, my bad. So that 1 picofarad is good enough. Let's keep it 1 picofarad. And then for now, let's stick with 200 picofarad, but you can go lower. This one can go to half a picofarad or even lower. Depends on what let's say technology node is used for chip design. I'm just trying to give a illustration here. It doesn't mean these are the best choices in terms of numbers. So this is 200 gain realized, and now these are the kind of capacitor with the proper sizes that they can be implemented in a chip. If need be, lower values to help with better implementation in a chip. And the nice thing is, while there are still variations for the absolute value of C2 and absolute value of C1, the good thing is if they are implemented, first they take a much less area compared to realization of resistors. These small capacitors consume a much smaller area. On the other hand, if they are implemented close to each other with the same approach, then ratio of C1 over C2 variation is very small. So instead of, let's say, 20 to 40% variation for the value of absolute value of resistors with these kind of sizes that are going to be humongous, for the ratio of C1 over C2, the variation over temperature or other parasitic effects can be controlled to less than or equal 0.1%. So it's very accurate actually amplifier in terms of the realized gain. So it's very capable, sort of a stable amplifier as long as the design is proper and clocks are properly applied, which it will come with its own nuances, of course. So I just wanted to say that basically the ratio of C1 over C2 in this circuit, if it is done right, just define the non-inverting gain or positive gain. Now, imagine if you want to realize a negative gain. So inverting amplifier like this first architecture. Now, what is the approach? Interestingly, it would be very similar approach, except the only change I need to do if I copy paste the circuit so that I don't touch the first circuit here. So I'm going to show you a very simple change so that it will convert this switch capacitor non-inverting amplifier to a switch capacitor inverting amplifier, and that would be this change. So I'm going to change the circuit like this. I'm going to change it in this sense that I'm not going to change the relationship between clock 1 and clock 2. necessarily, but I am going to disconnect T4 from transistor. Let me just make sure I find the right color. Okay, I'm gonna disconnect the gate of transistor T4 or the switch T4 from clock 2, and I am going to, so this was connected here to clock 2, so I'm gonna disconnect it, and then I'm gonna connect, and I'm gonna also disconnect T1 from clock 1. Now what I'm gonna do is I am going to connect T4 to clock 1 and the gate of T1 to clock 2. So just a simple change, basically swapping the clocks applied to gates of T1 and T4. See what's going to happen now. During the time or T period T1 in which we have clock 1 on and clock 2 off, so same as before. When clock 1, so when clock 1 is on and clock 2 is off, so what happens is now T1, so this is the inverting amplifier, so inverting amplifier switch-capacitor amplifier, basically switch cap. So in this case T1 is in this case T2, T3 and T4 are actually on, not T1 anymore. So T2, T3, T4 on, and we have T1, so we have T1 and T5 off. Okay, so now what's happening? The circuit looks like this. So we have open, so there is no connection to C1. C1 is effectively via T4 is now grounded. So this is T4 that is on like an ideal switch with a equivalent resistor of 0, so it's short. So we have C1 grounded on one side, on the other side C1 is connected to negative terminal of op-amp, which is at virtual ground effectively in a steady state. So we have 0 here as well. So on both sides of C1 we should end up with 0 in this duration, and then C2, on one side T2 is on, which means the output again shorted, the negative terminal is shorted to the output. Cap C2 on this side is connected to virtual ground, and then T3 is also on, which means cap C2 is also shorted on the other side, so is also shorted to ground by transistor T3, which is on, and then T5 is off, so there is no further connection. So T5 off, and then we have connection to the output of op-amp, Vout. So the Vout is 0 in this duration, of course, because Vout is connected to virtual ground, and the only thing that is happening is both capacitors are forced to completely get discharged. So C2 is discharged, C1 is completely discharged. In this duration, VC1 ultimately or quickly gets to 0, VC2 gets to 0. There is no charge remaining on plates of capacitors. Now, so that's the status during the duration when clock 1 is on. Now, when clock 2 is on, which means clock 1 is on, when clock 2 is on, which means clock 1 is off, then what happens is T1, T5, they are on, naturally T2, T3, T4, they are off. So now T1 is on, so Vin is connected, so Vin is now connected to via transistor T1 that is like a short switch, so it switches on is like a short circuit, and T4 is off, so there is no connection in T4, and we have cap C1 connected to input negative terminal of ideal op amp, and then with the same argument there is no transistor T2 that's open, but then T5 is shorted while T3 is open. So therefore the circuit simply looks like this: C2, switch T5, and then we have V out. So now from the initial state that there is no charge across the caps, so zero charge here and zero charge here, what happens is quickly the circuit should get to a state in which on this side of both caps we have virtual ground or 0 volt, and on the other side we should end up with plus V in with this polarity sort of appearing across C1, so enough charge need to accumulate on the plates of C1 to result in V in across C1, and for C2 we will end up, because of the direction of charging, which will be this direction, so V in injects a charge that can only go this way because it cannot go any other way. It can't go through the input of op amp, so the input terminal is effectively infinite impedance. Now when it's going with when this current goes through C1, it would accumulate the charge with this polarity. It would accumulate also a charge with, again, this polarity across C2, which is counter the polarity of V out, because V out positive with the definition of V out is now at the negative assumed polarity for the accumulated charge across C2. So that negative gain is coming from that observation. So but we go back to the gain law of conservation of current and charge. So whatever current going this way should go this way, so whatever charge accumulated should be the same there. So what we can say is, during this time, same current, same charge, so we get to effectively Q of 1 C1, let's say, should be equal to Q of C2 during this duration. So we end up with just voltage of C1 times the cap C1 equal to voltage of C2 times the cap C2. But be careful that now we can substitute, knowing that VC1 is V in. So let me write it this way so that there is no confusion. Knowing that VC1 is V in and VC2 is just minus V out, so we get effectively that voltage gain of this circuit, which is V out over V in, is now minus C1 over C2. So same as before in terms of absolute value, C1 over C2. So C1 over C2 still defines the gain, but the only thing is now with this adjustment in application of the clocks, we realize a negative gain here. So it's an inverting amplifier scenario. Okay, so now we understand that this circuit, with simple modification of how we apply clock 1 and 2 into into the gates of T1 and T4, then we can change the circuit into inverting or non-inverting amplifier circuit with the same absolute value gain, C1 over C2. Now, one last thing. So we know how the circuit is working, we know what kind of gain it's realizing, we know the benefit of it in terms of the size, the actual size that this circuit occupies on a chip on silicon substrate would be much smaller, or silicon footprint, as they say, for this circuit on a chip or substrate would be much smaller than if somebody wanted to do it with 10 kilo ohm resistor and 2 mega ohm passive resistors like this, which would have huge silicon footprint, which is pretty expensive and also inaccurate, and with lots of parasitic effects associated with the caps, equivalent cap that is coming with resistors and other variations as well. So a lot of non-idealities. This one has its own nuances, as I said before. For example, we need to be careful about how to model the switches, how do we design the circuit in such a way that the non-zero resistive effect of on switch can be neglected, and also the non-infinite open resistor switch, let's say open switch resistor value also can be assumed to be practically infinite. And also the clocks, we need to be very careful. These two clocks are designed with respect to each other so that practical offsets or let's say variations in terms of let's say pulse per million of variation of these clocks or jitters basically would not cause major problem in the circuit. So it's very important to make sure clock 1 is on, then clock 2 is off. When clock 2 is on, clock 1 is off. And sort of other practical concerns. But this circuit footprint on silicon is much smaller and it has much better behavior in terms of non-ideality and potential variation if it is well designed. Now, one last thing. Because this circuit is effectively realizing this passive resistor base inverting or non-inverting amplifier, we should be able to also say what is the equivalent resistance or resistor that is observed for C1 combined with switch and for C2 combined with switch capacitor. Effectively, we are realizing switch cap or switch capacitor based resistor. So it's like this. During the period, during the time, let's say this is clock 1. I'm going to show you clock 1 in a sort of magnified view. So during the time that we have clock 1, it looks like this in a sort of magnified view, and it keeps going on. So this is one period of clock 1, let's say T clock or period of clock, which is obviously 1 over frequency of clock. So T is in let's say second or microsecond. F of C or the frequency of clock is on megahertz or hundreds of kilohertz, for example, or even more. So for clock 2, we have something like this. I'm going to show with different color just to make it easier to be seen. So for example, let's say we go with green. So clock 2 looks like this clock. Okay, so you can see that during the off time for clock 1, clock 2 is on, and there is some gap between the corresponding rising falling edges so that we make sure that there is some margin if the clocks end up to suffer from some offset, so that there never be an overlap between them. So this is the scheme, and the period of both clock is just TC, which is 1 over FC. So they have the same period and frequency. Clock design is very important matter in the switch capacitor circuits. Okay, so during the one period of the clock, the circuit feels, or the Vin feels, as if the total amount of current that it provides is the amount of current that it provides to charge C1 up to Vin appear across its plates. So it's as if we would say average current, or basically the current observed in one period, which is always repeated, is equal to the charge transferred to cap C1 divided by time, which is the time that we are doing the averaging, which is the time of period of clock. And the charge is just the value of C1 times the voltage that appears across C1, which is Vin over TC. So in summary, I can say is just Vin over TC over C1. You can see that we are saying current at input is equal to voltage at input divided by some constant. That reminds of effectively a resistor. So we are emulating a resistor here. And that equivalent resistor emulated is what we refer to as switch-capped or switch capacitance-based resistor implementation. So R equivalent in this circuit for the resistor that is here effectively is just effectively TC, the period of clock, over the cap C1, or alternatively 1 over C1 times frequency of the cap. Think of it this way. If I go with, say, C1, as I said before, as 1 picofarad, as an example, and if I go with FC1, or the frequency of the clock, to be, say, 100 kilohertz, as an example, then, of course, this whole thing, let me make sure I'm not missing something. Okay, so let's say if I go with 10 megahertz, for example, then what's happening is we get 1 over 1 picofarad, which is 10 to the power minus 12, and we get to say 10 megahertz, which is 10 to the power 7. What we wanted, for example, is just to get to a gain of, the example we tried was, say, we wanted to have C1 as an example that I covered. We wanted to have C1 to be C1 200 picofarad, C2 1 picofarad. I'm just trying to give a practical example. So C1 is 200 picofarad, and let's say I go with a clock of 1 megahertz as an example. So correction, 200 picofarad is 2 times 10 to the power negative 10, and 1 megahertz is 10 to the power plus 6. So we end up with effectively 10 to the power 4 divided by 2, which means 5 kilo ohm. So interesting. Effective R equivalent number 1 is 5 kilo ohm that is realized in this circuit. So that would be for the equivalent resistance that is observed here effectively or emulated. The emulated equivalent resistor that is observed for C2 combined with switches would be computed the same way. So we can say R equivalent 2 is again TC over C2, or it is 1 over C2 over FC. FC1 and FC2 is the same thing. So we're going to have the same frequency for the clock. So now C2 is 1 picofarad in the sort of this example that we wanted to gain of to have an absolute gain of 200. So FC remains 1 megahertz, same frequency. What are we getting? We are getting, of course, we are getting 1 picofarad 10 to the power negative 12, and then 10 to the power 6. So we are realizing a 1 mega ohm resistor effectively. So that's just 1 mega ohm resistor. So the circuit effectively realizes a 5 kilo ohm resistor here and 1 mega ohm resistor here, which then 1 meg over 5K will give us the gain of 200 that we wanted, either in inverting fashion or non-inverting fashion. Okay, I hope that this example and sort of a switch capacitor amplifier tutorial and walkthrough is helpful in terms of understanding how the concept of switch capacitor is working, what are the benefits of it, why we need them in practical implementation, especially for chip design, for the amplifiers, and what are the issues potentially. I hope this is helpful. I'll cover more examples in the future videos. Thanks for watching.